In this video, we're going to look at some of the important content that we discussed in Chapter 1. We're going to look at a few examples that will help us cover this content. So we're going to start with the functions given by formulas. In this example, it says a population of people in a small town can be modeled with the function p equals 17,300 plus 104e to the 0.03 t, where t is the number of years since this model was developed. Use functional notation to represent the initial population and calculate that value. So initial population would correspond to a t equals 0. So our function notation would be p of 0. So we're inputting 0 to the function equals 17,300 plus 104 e to the 0.03 times 0. So we're inputting 0 for t. So what this is saying is the population at time t equals 0. Using our graphing calculator, we can calculate this value. P of 0 equals, we want to enter that on the calculator, 17,300 plus 104, and to bring up the E button, we hit second, and then this ln, this natural log button, brings up E, and now we enter the exponent 0.03 times 0, and we get 17,404. This means that the initial value at time t equals 0 when this model was created is 17,404 people in the town. Use functional notation to represent the population of people after 4 years and calculate that value. So the only difference here is for t, we're really going to enter 4. So we're going to find p of 4, saying we're going to enter 4 into the function for t. That would equal 17,300 plus 104 e to the 0.03 times 4. Using our graphing calculator, we can again calculate that value. 17,300 plus 104 e to the 0.03 times 4 gives us this number. P of 4 equals 17,417.2. And so I would say, since we're talking about people, rounding that to the nearest number, nearest whole number, P of 4 equals 17,417 people. That means after 4 years, there will be 17,417 people. In part C, we want to explain the practical meaning of P of 10. When we're looking at function notation, this is always talking about our output. The number in the parentheses is talking about our input. Our output currently is population, and our input is time in years. So I would say this represents the population after 10 years. And notice that's not asking us to calculate that. It's simply asking us what this notation means. Moving on, the next section we talked about some functions from tables. This says the height of a cannonball h equals h of t that is launched from a cannon is given in the table below, where t is the time in seconds since it was launched. Use functional notation to represent the height of the cannonball after 3 seconds. So we're considering this column here, 3 and 45. T is our seconds, 45 is our output, I would say h of 3 equals 45. What that is saying is the height at 3 seconds would be 45 feet. What is the average rate of change from 3 to 6 seconds? So here, we're going to look at the change between these two columns. The average rate of change always equals the outputs, the change in the outputs divided by the change in the inputs. So looking at the change in these outputs, 60 minus 45 over 6 minus 3. Our change in outputs is 15. Our change in inputs is 3. And 15 divided by 3 would be 5. Now if I was to ask you about units, and it should have said in this problem, but let's assume height is in feet. When we find the average rate of change, that is always our output per our input. Or this would be 5 feet per second. What that number is telling us is every time the input increases by 1, we expect the output to increase by 5. Or in other words, each additional second would make the height of the ball increase 5 feet. So if I wanted to estimate the height of the cannonball after 5 seconds, in other words, I want to find h of 5. Then I would say that this is approximately the height at 3 seconds, which is 45, plus to get from 3 to 5 seconds, I'm going to do 2 times 5. An increase of 2 seconds at 5 feet per second. So I would say h of 5 is approximately 45 plus 10, or h of 5 is approximately 55 feet. So again, the reason I'm doing this here, that's coming from this number, the 5. I'm increasing from 45 at t equals 3 to 55 feet at t equals 5, or 5 feet per second. 5 times 2. The next thing we want to discuss is functions from graphs. In this example below, it says the graph shows the population n equals n of d in thousands of animals of a particular species as a function of the date d. We always want to remember, this line gives us our input, these are our outputs. Describe how the population changes with time. In other words, as time moves on, what happens to the population? Well, I would notice here that the graph is actually concave up, so the population is increasing fast at first. Then the graph shifts to concave down, so the rate that the population is increasing is slowing down. So I would say the population increases fast at the beginning, but the rate of increasing slows down over time. Where does the graph appear to be concave up? Well, concave is referring to basically the way the graph is bent. So I would say during this time, the graph is concave up, but during this time, the graph is concave down. So if I was to answer where does the graph appear to be concave up, to me, at this little point here, this is where our bend starts to occur. So all during this time, I would say we're concave up. So from 1970 to 1985. When does the population appear to be growing the fastest? Or in other words, where does the graph appear to be the steepest? And again, I would say that kind of appears to be during this little time right here, where the graph actually is increasing the fastest. So I would say it appears to be about 1985. Does this function appear to have a limiting value, and what does that appear to be? The limiting value will always refer to the function value. If as time goes on, the graph appears to approach a certain number, that is the limiting value. So see here how this graph appears to be leveling off. So I would say yes, it has a limiting value. If I look back for that function value appears to be 140. And in this case, our output is in thousands, so 140,000 animals. The last thing that we talked about in chapter 1 is functions from words. And this is where we're going to create our own function. So in planning for a party, you want to calculate a reasonable budget. You know your supermarket charges 75 cents per soda and $2.25 per hamburger. Write a function that can be used to calculate your total budget if you know you are only going to purchase sodas and hamburgers. Define each variable. So here we're really talking about three things. Let's use B, an uppercase B, for budget, because that's going to be our output. A lowercase s for sodas, that's going to be our input. And a lowercase h for hamburgers, because again, that's going to be our input. So we're using these two things to determine our budget. So I would say budget is a function of the number of sodas and hamburgers. To calculate it, we would do 0.75 for the 75 cents times the number of sodas, and we would add to it $2.25 times the number of hamburgers. Now we could enter any number of sodas and hamburgers and calculate the budget. So use functional notation to represent the budget for 16 sodas and 8 hamburgers. Compute the budget for this situation. So our functional notation, our budget, is a function of hamburgers and sodas. So our budget is determined by 16 for sodas and 8 for hamburgers. That would equal 0.75 times 16 plus 2.25 times 8. Possibly you could do this by hand, or you could come back to your graphing calculator. 0.75 times 16. This number is 12. 2.25 times 8 is 18. And if we add those two together, B of 16, 8 equals 30. Or in other words, our budget for 16 sodas and 8 hamburgers should be $30. And that's it.